Hello, everyone. Welcome to the session. So we have Magdalena Stenius presenting us on understanding the carbon footprint of machine learning uh, right now. So just to give an introduction about Magdalena, so she is a machine learning engineer at Valohai, and she's also an active member of the Finnish female and non-binary programmer community, as well as a co-host of Turku.py, which is her town's local Python meetup. She's very enthusiastic about environmental topics and fairness in machine learning and artificial intelligence. Let's give it up for her to have this session. Over to you, Magdalena.
Thank you so much, Shruti. So thanks for the introduction. And I'm very excited to be here talking about this topic to all of you today. So as Shruti mentioned, my topic for today will be understanding the carbon footprint of machine learning. And this will be a quite technical talk. I'll try to make it easily accessible for also those who don't work in technical roles. So let's start off with a little bit of the background. I'm born in 1996. And when I was growing up, throughout my childhood in school, we would keep hearing how important environmental issues are, how pressing the situation is. We were being instructed, even as small children, to always close the tap when we didn't need more water, to, for example, recycle our waste, and also to never leave the lights on when you left the room. And this kind of background has really stuck to me, even as an adult, as our generation is now growing up and becoming the new workforce. I think all of us have this impression of we're trying to do something for the climate. MIT recently published a technology review stating that training a deep learning model, especially these kind of natural language processing models that are text generating, that are becoming more and more popular, can cause up to the same emissions as 5 cars would cost during their entire usage lifetime. Here are the statistics of that example. So here are some examples of deep learning models that are basically text generating models, deep neural networks, and their carbon footprints. You can see that next to the carbon footprints, there are also the cost of the compute that is used for only one training of these models. Those of you who are familiar with machine learning as a concept know that when you are building a machine learning model, you will be training it over and over again multiple times. And you can imagine that if the cost of one training is this, then the cost of the continuous training process that these models are going to is huge. And this is my second reason for having this talk today. If you're not completely sold to the idea of saving the planet yet, maybe you are in a business decision-making role, or you need to convince the business decision makers in your company, then you can always reason that saving the planet, or actually optimizing your software, optimizing your machine learning models in a way that they become more energy efficient, is also a great way of saving money. Green software has become more and more commonly used and seen word recently. Some common topics in green software are optimizing code and infrastructure. For example, just yesterday, the biggest Finnish newspaper, Helsingin Sanomat, published an article where they were describing how one of the big bus companies in Finland had reduced the cost of their system, of their IT system, by 400,000 euros per year by modernizing the code and reducing the infrastructure needs they had. That's a lot of money, but they also saved a lot of energy while doing this. And we hope to see more and more success stories of companies modernizing their code base, making their code and software products more efficient and green over the coming years. One of the topics has also been the choice of programming language. We can, for example, see examples of how the programming language Perl consumes 80 times the electricity of the programming language C. And then there is also the topic of transferring data. If you have a website, one of the ways of measuring a website's carbon footprint is to measure the size of the files being sent over and then measure how many users are visiting your page during the day. And for example, the American Council for an Energy Efficient Economy had done a research which said that it takes 5.12 kilowatt hours of electricity per gigabyte of transferred data to actually send over these website files. So minimizing your files, minimizing perhaps very large images is a great way also of making your web software more green. So then we get to the case of machine learning. I see that there are some questions in the chat, but I'll try to go through the talk and then we can talk more about those at the end of the talk because my brain can only go on one track. Sorry. Yes, so the case of machine learning. Machine learning is in many ways different from software or traditional software development. And one of those ways is, as I described a bit earlier, that machine learning models or machine learning projects are basically mathematical models where you are baking in data into the model to teach it to behave in a specific way. And this is called model training. And model training is an iterative process where you are running the data into the model multiple times over and over and trying to get it to learn from that data. And this is very compute heavy work. So you need a lot of compute power to be able to do this calculations that it takes. And there are also special hardware requirements for machine learning model training. One of the examples is that you often will use graphic cards, so GPUs. This is not hardware that is always available in regular computers. Another thing that makes machine learning a special case in green software is the kind of topic of data. So data storage and massive data sets, which are being used in this model training. But then again, there are also similarities to software development in machine learning. For example, model consumption. A data science or a machine learning model can, for example, be consumed like a regular API over HTTP. So this is a similarity to regular software engineering. Another kind of topic that has been popular in the field of machine learning lately is this tiny models and edge computing case where you would have limited hardware running, for example, on a drone or on a camera somewhere in the jungle, trying to recognize different wildlife or recognize forest fires based on images. In those cases, you would need to really optimize the models you are using so that these tiny edge devices are able to run them efficiently and they don't need to be charged very often. A little bit about why I started working with this topic. I work for a company called Valohai. We are a machine learning operations platform. And every month, there are more than 100,000 machine learning models trained on our platform. So we are vendoring compute from the major cloud providers as well as supporting customers on premises. And our cloud providers include AWS, Microsoft Azure, and Google Cloud. And as more and more data science teams are looking into climate issues, and for example, even physical product teams who have aspects of machine learning in their products, they're looking to be able to say to the users that our products are carbon neutral. For example, we have a car that is smart and it's carbon neutral. And this is the case one of my friends who is working as a data scientist had. She was telling me that she would like to have data science tooling where the climate footprint or the carbon footprint of the data science tooling would also be visible to the data scientists so that the product could be entirely carbon compensated. So this is why we started looking into if we would be able to show the carbon footprint of these machine learning model trainings run on our platform. The first intuitive thought that came to our mind is that we are already using these cloud provider UIs and APIs, and we are vendoring their compute. Wouldn't it be awesome if they would just show their carbon footprint right in these tools? And it has become more and more common. For example, AWS just published their carbon footprint tool, which is also in this picture here. So basically, if you are using cloud compute from AWS, you can go to your billing console and you can see the carbon footprint of your compute and storage that has been run on AWS. But there were some challenges in this approach. One of the main challenges is, what is the business incentive of these cloud providers to actually show the carbon footprints? Of course, they would like to show very good numbers, kind of showing that they are very green and very efficient. And also, they want to kind of show that they are doing a lot of work to compensate for these carbon emissions to make their users happy. Of course, this is a great thing and a great trend, but this also leads to a situation where they are more likely to kind of show a little bit of a limited perspective into the actual carbon emissions of these services that they provide. So as I said, we have a lot of models being trained on our platform every month. Our AWS is our own main infrastructure location. And we are using, our AWS bills are up in thousands of euros each month. And when I opened our billing console and our carbon footprint estimations, it looked like this. And first, I was sure that there must be some technical problem since this feature is still very new. But it became clear that the reason our emission statistics look like this is that most of our infrastructure, or almost all of our infrastructure, is located in a region called EU West 1. And EU West 1 happens to be a region that is compensated by energy credits. So this means that when AWS is using energy in this region, and that energy is non-renewable, they are compensating it by instead pumping out renewable energy into the grid. This does not mean that there are no emissions in this region. This just means that they have in some way compensated for that. And I wasn't happy with this view because this doesn't say anything about what is actually going on under the surface. So we decided to dig a little bit deeper. Oh, and I also have one tip. If you are on AWS, indeed, there are these regions where compute is compensated. So if you have the possibility, look into those compensated regions and use them, because then you can also get a graph that looks like this. However, I wasn't satisfied, so let's keep going. Now we decided to dig into what the carbon emissions of compute are anyway. When we are talking about carbon emissions, we can use this tool called the GHG protocol, or the greenhouse gas protocol, basically, where emissions are divided into 3 scopes. Scope 1 means direct emissions of the company facilities and vehicles. And scope 2 is purchased electricity. And scope 3 are, for example, the goods and services purchased by that company. If we try to fit these 3 scopes of emissions into a data center operator, we get scope 1 being the natural gas and diesel that are used by the data center, scope 2, which is the purchased electricity to the data center, and scope 3, which is the hardware manufacturing, basically the emissions that are created when those servers are being manufactured. If you're interested in reading more, you can read more in the link in the slides. So let's look into electricity. The main things that impact the electricity consumption of a server is the processor load and the memory usage. This is why it is also important as part of your carbon emission strategy to try and optimize your code. If you're familiar with big O notation, you already know how large differences small changes can make. So that's also one tip I can share for you. Then if we're looking into what the carbon footprint of electricity is, there are a few different kind of topics that need to be addressed. One of them is the region in which that electricity is consumed, and the other one is the data center setup. Let's dive into some of those concepts. The first word that will become visible when you start Googling data center carbon emissions is PUE, or power usage effectiveness. PUE is basically a word for measuring how much of the total power going into the data center is being used to power the servers. So the PUE comes from the total power in divided by the power used by the servers. And the optimal value in this case is 1, because we would like to have a data center where all the power that is going into the data center is going directly into the servers. That would be very efficient. And this is also one of the great things with cloud compute. The average number or the average PUE value for on-premise data centers, meaning maybe a little bit older data centers in the US, is 1.7, whereas Google reports numbers as impressive as 1.12. So you can see that these hyperscale cloud vendors, because of this massive scale that they're operating in, they are able to really optimize their data centers in a way that almost all of the power going into the data centers is being used directly to power the servers. And this is also my next tip. If it's possible and feasible in your case for your project to use cloud compute instead of having a company-owned on-premise data center, do use the cloud compute option, because cloud compute in almost all cases is more efficient than on-premise compute. The next concept I wanted to talk about is electricity carbon intensity. Electricity carbon intensity means how many grams of CO2 is produced when 1 kilowatt hour of energy is produced. And this does vary quite a lot depending on the region. You can see on this map shared by ourworldindata.org that the carbon intensity of electricity varies a lot depending on the region the electricity is produced in. For those of us who are in Europe, it's a general recommendation to look at the regions in the Nordic countries where the carbon intensity of electricity is low. This means that for the same amount of consumed electricity, the emissions will be lower. So this is also a tip I have for you. Choose greener regions. If you have the possibility and you are using cloud compute, pick those regions that are more energy efficient or more that have a lower carbon intensity. And now into the hard parts. How much electricity is the machine consuming when it's training our model? The next challenge we ran into was, can't we just ask the machines? If I have a Mac computer or, for example, a Linux computer, there are programs for those computers, such as Stat or PowerTop, that can easily display how much electricity consumption or how much the current consumption of electricity is at each given moment. This screenshot is from Stats on Mac. So we would like to know at any given time, for 1 hour of running the computer at a certain CPU level, or CPU stress percentage, how many kilowatts are consumed? The challenge here is that when we move into the world of cloud compute, we run into virtualization. You don't get to access the bare metal under the server anymore straight away, but it's hidden under abstractions and abstractions of virtualization. So luckily for us, there is a team called Teads Engineering who have done a great work with building a data set of AWS EC2 energy consumption. For those of us who are not familiar with cloud compute, AWS offers cloud compute in the form of machines called EC2. And the way that they got to these results was that they started looking at AWS instances and concluded that according to AWS documentation, each instance can be directly mapped to dedicated hardware. This was true for all instances except for the T instance family, because that family has a burstability aspect in it. So for example, if we looked at a machine P3 8x large, it has exactly half of the resources as P3 16x large. The next step of this methodology was that they used tools such as turbostat, which is measuring the Linux statistics of CPU usage and, for example, power consumption on AWS bare metal instances. So there are a few instance types on AWS that do expose hardware, and they are called bare metal instances. So they ran tests using tools such as turbostat on different load levels on these machines. From there, they were able to map those results to virtualized resources, such as virtualized CPUs, and from there, generalize them to other instance types as well. And this is the result. So this is the Teads Engineering dataset of EC2 instance power consumption. It's open sourced. It's under the Creative Commons license. And anyone can access it and use it. So this is actually a very great open source contribution on their behalf. Then on to the next scope, or manufacturing. So according to Udit Gupta and others, the majority of data center emissions are actually coming from hardware manufacturing. The challenge here is that we would like to know the emissions per component. So for each component in the server, what are the emissions of that? A company called Boavizta has done an amazing work at building this hardware emissions dataset, where they're gathering different servers, also laptop computers, also monitors, even mobile phones, and documenting their manufacturing emissions. So I really recommend you to take a look at this dataset. I will add a link to it later on, and see how the different how much the different tooling that we are using every day takes to manufacture. In this pie chart, you can see the scope 2 emissions, or the usage emissions, in light green, and scope 3 emissions, or manufacturing emissions, as darker blue. And the estimated lifetime for one of these servers is around 4 years. So let's take a closer look. Again, let's look into the Teads Engineering dataset to see how they were calculating the hardware emissions in their dataset. So Teads Engineering had this, so to speak, a naive approach of building the dataset, that they assumed that each hardware or each rack server in a data center is composed of a, so to speak, minimal rack server setup, which has a carbon footprint of 1,000 kilograms of CO2 equivalent. And on top of that, depending on the server itself, and its components, you would add various extra amounts depending on what it's composed of. So here's an example of a computer that is, or a server that is very often used in machine learning or deep learning. So the AWS EC2 P instance family is an accelerated computing instance family, and these are often used in machine learning because they have these accelerated or accelerators or GPUs attached to them. So in this example, we have the minimal rack server, which is 1,000 kilograms of CO2 equivalent. On top of that, we can see from AWS documentation that this instance type has 96 virtual CPUs, and they are using the specific processor, Xeon Platinum 8275CL. When we look into that specific processor details on Intel's page, we can see that that processor is able to thread 48 threads at a time. This means that 48 virtual CPUs exist on one physical CPU. So this means that if we have already one CPU defined in the minimal rack server, we only need to add one more to the calculation. We also have some extra memory, dynamic random access memory, and we will calculate for the amount exceeding the minimal server amount, the emissions per gigabyte. In addition to that, we have 8 NVIDIA A100 Tensor Core GPUs. And for each of those, we just add 150 kilograms of CO2 equivalent. And lastly, we also have some extra storage, 8 1000 gigabyte NVMe SSD cards. So let's add 8 of those. And the total manufacturing emissions of this type of server amounts at 4,778 kilograms of CO2 equivalent. This number is then divided over a 4-year lifespan, but you can still see how this kind of production of servers amounts to a massive amount of emissions. And lastly, we get into this very engineering problem of this methodology. We wanted to publish these numbers in order to share with our customers the emissions of each of their machine learning trainings. The image you see on the right side is a screenshot from our platform. So each time our customer teams run a machine learning training on our platform using AWS instances, they get this optional notification window where you can see the estimated emissions for that training. In the estimated emissions, we are also adding some detailed information about possible renewable energy credit compensation or other similar types of compensation. And we are building this heavily on the Teads Engineering dataset of carbon emissions of EC2 instances. So the challenge here was that as engineers, we really want to get the exact numbers. We are taught to be precise and that everything has to be exact and that there would be a pure right result to this question. How much carbon did I create by running this machine learning training? But we found that in this topic, it was really hard to find a single perfect answer or perfect approach, since there are so many changing variables in the equation. In the end, we were satisfied by letting the customers know that this is an emissions estimation and trying to do our best to really explain how this data was gathered. One of the more questions that still remains is the carbon emissions of object storage. On our platform, data is mostly used in the form of S3 storages, but AWS doesn't expose any of the internals of its data storage services. However, we can conclude that energy consumption of storage is relatively low. So for example, 1 terabyte of SSD storage, the average consumption is only 2.2 watts per hour compared to the total of 3,782 watts per hour of the machine we just looked at. So storage is in that way electrically cheap, cheaper than compute. However, accessing the storage, reading from it and writing from it can be more expensive. Based on this research that we were doing this spring, we created an open source repository and a project called Valohai Watson. It's a Python package. You can easily install it via pip. It's open source, it's available for everyone, and it's leaning heavily on the Teads Engineering dataset. Using this Python package, you can easily get an estimation for your carbon emissions given a specific AWS EC2 instance type, the region it was run in, the hours, and the CPU load percentage. And now looking forward, the next trends in the field of sustainable software or green software are definitely looking into the environmental impact beyond greenhouse gas. So not only looking at the carbon footprint, but also looking at, for example, what impact does the manufacturing of chips or these microcontrollers have in the region that these minerals, for example, are gotten from. We also would like to make a special special note of the Boavizta manufacturing emissions dataset. We would really hope to see it grow and more companies contributing to it, and also more and more of the hardware manufacturers really adding this transparency of the hardware's environmental impact and carbon footprint. Another topic that I would really also hope to see grow would be that there would be more standardized procedures for the carbon compensation. For example, Google Cloud says that they are completely carbon neutral. So they are compensating their carbon footprint in some way, but you have to be an expert in the field of climate change and carbon footprints and carbon compensation to really evaluate if these methodologies that these companies are using are good enough, or are they following a specific standard in the field of compensation. So this is also one of the topics I would really like to see more focus on in the future. And that was everything I had today on this topic, and I'd be really happy to try and answer some of the questions you might have. So thanks a lot for listening, and yeah, really happy to be here.
Thank you, Magdalena. That was a great session, and it was a lot of intuition into understanding how it does affect everything around us and how we can work towards it. So we can get on to the questions. So we had our first question from Anirudh. Why do different coding languages cause carbon footprint differently?
Yeah, so this has to do, as Mary already said in the chat, this has to do with the different efficiencies of the programming languages. So when a computer is executing different programming languages, that execution process, or perhaps compiling or interpreting those different coding languages, takes up a different amount of resources. Very often, you can also see, as Jocelyn pointed out, that you can have low-level code that is very efficient, like, for example, C, where you have to do everything yourself. And then again, like higher-level code, such as, for example, Python, where everything is pretty much included and it's very easy and readable to write. But it takes a lot more to actually run on the computer.
Yeah, thank you. Hope that clears your doubt, Anirudh. Do let us know if you have any following questions. So the second question that Anirudh had is, companies incentivize profits. Is there a sustainable model that incentivizes low carbon emissions and profits?
Okay, let's see.
He wants to understand how, is there any model where they're also incentivizing lower carbon emissions along with the profits?
I'm not really sure if this answers the question, but for example, like when you are, one of the great ways of reducing your costs in software projects is kind of looking at your resources and seeing if you have any unused resources or underutilized resources. And for example, checking your cloud compute underutilized resources, you can also really reduce the costs of this cloud compute because you don't have unnecessary servers and storage hanging around. So this is an example of how really kind of being climate smart and being monetarily smart are both hand in hand for a company. Yeah.
Yeah, that makes sense. So Michelle wants to know if there are any particular books or resources to follow that you would like to recommend for learning more about offsetting carbon emissions for machine learning.
That's a great question. I think I would also really like to read a book on that. The problem is that this is such a new topic and so, like a field where there are so many like constantly changing parameters that I think there are no very accurate descriptions of this topic in a book yet. Oh, Mary says, write the book. Oof, I don't know. So what I would really really recommend is just getting your hands dirty, like digging in, trying to yourself estimate, for example, looking into how much electricity your computer consumes, looking into how much electricity or how much emissions was created when manufacturing your own computers. Checking, for example, how long it takes to run the models on your computer, like how much resources do they take up, how much of your CPU they take up. These are the stepping stones of like understanding what these topics are built of. And then once you kind of understand that a bit deeper, then it's easier to talk about their impact on the carbon footprint of the product total and also how to maybe compensate for that. But if these topics scare you, then maybe also look at the tools that are already available by the cloud providers. I know I was a bit skeptical about the AWS carbon footprint tool, but I think it might be helpful for some of you.
That's great. I like Mary says, write the book, be a pioneer. That's great. That's some great audience right here. So that's all the questions we have right now. Does anyone else have any other questions for Magdalena? Mhm. Um, Looks like that's all we have. Magdalena, do you want to give any closing comments, or if there is any link that they could follow onto your work more and continue to follow you, or do post in the chat? That would be great. Yeah, if you have any closing remarks, we
Yeah,
can
I
talk
mean,
about
I can absolutely share the Teads Engineering blog series on this because that's, I think, a really great way to start. And I'm a big fan of their team and their work. So let's see. This is the blog. Oops, I don't know if you can see that. Did I send that to everyone? Maybe.
Yeah.
Okay, great. And also, yeah, Mary, I really wanted to comment on, yeah, the older computers are more inefficient. And as you said, like you were asking about the green cloud and Google's document on how they have zero emissions. So one example of like Google Cloud using kind of resources is that they, for example, have data centers in regions where there can be like times of the day where there is no power available. For example, if you have solar power and then there's like a few hours in the day that you can't use solar power, at those times they would use, if I hadn't understood correctly, I mean, you can find more information, of course, on Google's own documentation, but they can use, for example, diesel to power their data centers. And this means that when they do use those different kinds of like non-renewable energy, they try to compensate it by, for example, buying more renewable energy and like releasing it into the grid or things like that. Of course, it's a good incentive. Like it's a good thing that they are doing this, and overall the idea of compensation is awesome. But it doesn't take away the problem that there is non-renewable resources being used as part of this whole total. Yeah, and all of these, I mean, I'm really happy to see that all of these cloud providers, I mean, Azure, Google Cloud, and AWS all very recently published this carbon footprint tools in their consoles. So I think it's like a great development that they're trying to make it more visible, and in that way trying to kind of mitigate the effects it has. I think I will add the presentation somewhere. I don't know how you will share it.
The Women Who Code team, all the sessions are recorded, and we will be soon posting it on the YouTube channel, the recording as well. So Magdalena, if you want to share the presentation before that, you can go ahead and share it in the chat here. That would be great. But all the recordings will soon be available on the YouTube channel.
Okay, great. I can, yeah, because I have some links here. Let's see. I can't share it right now, but I will try to definitely share it maybe in the Slack or something. Maybe someone can find it there. Yeah.
Sure, that would be great. Anything else? We have only 2 minutes left. We're about time. Any other questions, anyone?
Yes. Is AWS leading in the space? All these different cloud providers have a bit different approaches. I would say like Google Cloud has clearly taken the compensating for all emissions very seriously, whereas AWS is then again trying to be carbon neutral by 2030. So I think all of them are working really hard. I think we should give them credit. But I think definitely Google Cloud is doing a lot of work to compensate for those emissions. Whereas AWS doesn't compensate, for example, for all the regions. They just happen to compensate that specific region that all of our infrastructure was hosted in, and that's why there was zero emissions for 2 years. That's amazing. Yeah.
That's so smart. Working on the carbon emissions from AWS. Yeah. Mary wants to know what's Azure doing and what's Apple doing about this.
Well, Azure was actually interesting because we do have some very limited like infrastructure of ourselves also on Azure, but their carbon tooling is only available for like enterprise plans, and we are not an enterprise, we're a startup, so I couldn't even access that part of their console. I don't really know how it looks like, but yeah. And for example, Apple, if you look at if you Google the different Apple products that are available, so the for example, the emissions of manufacturing Mac computers, then you can find a very detailed description of where the hardware or where the different minerals and materials are sourced from, and how much the carbon emissions for those are, and stuff like that, and what the company has done to kind of mitigate them. Yeah, amazing. I can stay here discussing with Mary for a long time, but
yeah, that would be great, Mary. I think enterprise is definitely really costly, and also as someone who's working in a startup, I understand it's not something I have not looked at that either. I've never been able to access some parts of the portal myself. So yeah, that would be great. And thank you so much for all the questions. We're about time. Thank you for being a great audience, and thank you so much for the session, Magdalena. I really appreciate educating us on this very important topic.
Thank you so much. It was my pleasure.
Thank you.